Some people are saying they did not receive the link. Only the YouTube link.
Pronto, Renato.
Okay. Am I in?
Sim.
Okay. Welcome everybody. Boa tarde. We are about to start our second talk of the semester. Today we're gonna, in a kind of continuing similar an analogous topic as we had last time with Chris. Wait, let me just make sure that I have everything here. Yes, we're gonna be listening from Rolf Jansen. A little bit about his history. He has finished his PhD in 2000, University of Groningen. And please, Rolf, if I say something inaccurate, feel free to correct me. He did a large spectrophotometric survey characterizing many aspects of nearby galaxies of several different morphologies. And since then has been working significantly on extragalactic, not only, but has done several important contributions to star formation, metallicities, reddening in nearby galaxies. After the PhD, he stayed for a brief period in the European Space Research and Technology Center, the ESTEC, and moved to Arizona State University, where he is right now, first as a postdoc, then became a research scientist. More recently, and what is, I think, very interesting, one of the topics that actually got us close together is that he has led or co-led a large program to observe the North Ecliptic Pole with JWST as a guaranteed time. And preemptively to that, the JWST, as you've seen from the previous talk, is going to be launched in a month, in December. And he was the PI of several ancillary proposals, with the Large Binocular Telescope for that field, and 2 Hubble proposals, one for the UV, covering that field as well. And this effort became a larger program, and there are many people involved now with data from X-rays to radio, and it's becoming a pretty famous, and hopefully it's going to be one of the deep fields for different types of research. And especially in that case, he's focusing on the time domain field, because one of the places that JWST is going to be pointing can monitor any time and has a lot of promise there, but it's not just time domain. And we in JPAS joined the group with, and you've probably heard about it, we call now JNEP. Nobody knows the name yet because we just got the data reduced during summer. But it was one of the pointings from the mini JPAS, similar to the mini JPAS, pointed that with all filters, and there's going to be an interesting collaboration with the group. So he'll talk a little bit about this today, and also about the Nancy Grace Roman Space Telescope that probably everybody knows as W1st, which is an upcoming mission that will be complementary to JWST with large field of view and so. So without further ado, I'll pass the word to Rolf.
Obrigado, Renato. And apologies that I will give this talk in English rather than Portuguese. So thanks for the opportunity to introduce and give a status update on a new community field for time domain surveys with the James Webb Space Telescope. In the second part of this talk, I will introduce the Nancy Grace Roman Space Telescope, its overall capabilities, and in particular, how it could study the epoch of reionization, also known as cosmic dawn. But I'll start with the take-home message of the first part of my talk. 2 weeks ago, Dr. Christopher Wilmer gave an in-depth overview of the JWST mission and its instrumental capabilities. Today, I will focus on the question of whether JWST can do a time domain survey and can do that sort of science. And the answer is yes, but only in a very special location in the sky. And the JWST North Ecliptic Pole time domain field is the very best place to do so. So what is this JWST NEP time domain field? It is a community field for time domain science, and particularly survey science with JWST, and a field in which observations now exist all the way from hard X-ray to long wavelength radio, all across the electromagnetic spectrum. Now, time domain science is a hot topic right now. In the next decade, the Vera Rubin Observatory and its LSST survey and the Nancy Grace Roman Space Telescope, formerly known as WFIRST, will survey the visible and near-infrared sky for faint objects that either vary in brightness or they vary in position, they move with time, and that includes also transients. This will enable time domain science in the solar system, in our galactic neighborhood, and also at cosmological distances. So it begs the question whether JWST can do time domain survey science, and if so, what would it add to these other surveys? As it turns out, over similar timescales and in a suitable survey field, JWST can survey variable or moving objects that are at least 3 magnitudes fainter than LSST can. And this is an unexplored magnitude regime for variability studies. Supernovae of various normal and exotic types would be detectable to extremely large distances. And the same is true for very faint and distant active galactic nuclei. But also stars and substellar objects could be found at these magnitudes. It is also an unexplored regime for detecting the motion in the plane of the sky of very faint objects in the extreme outer solar system and in our galactic neighborhood. And this might include early detection of interstellar visitors that pass through our solar systems, such as Oumuamua or Comet Borisov. The James Webb Space Telescope, Webb, is, however, not as nimble as Hubble, and it has much more stringent operational restrictions. So you cannot just point it very rapidly from one place in the sky to another place in the sky and come back over and over again. The sun avoidance, the power generation, and the shielding requirements of the cryogenic telescope, they restrict object visibility typically to 2 time intervals per year. Except that is for objects that are located within 2 small continuous viewing zones, or CVZs. They are centered on the north and on the south ecliptic poles. With only plus or minus 5 degrees of off-nominal roll angles allowed, as seen in the upper right figure here, the date of observation actually dictates the orientation of the instrument footprints on the sky for a given target, except again for targets located in one of these CVZs, these continuous viewing zones. So if we want to enable time domain science with JWST on timescales from minutes to over a decade, then a suitable survey field must be located within these CVZs. And this unfortunately means that existing fields from Hubble and Chandra and other missions won't do. So let's take a near-infrared look at the northern and southern CVZs. In these figures, I show low resolution and relatively shallow color composites that were constructed from 2MASS and WISE imagery that span much of the wavelength range of JWST's NIRCam. Even by eye, the northern CVZ on the left looks cleaner and emptier than the southern one at right, because the southern one contains, for one thing, the Large Magellanic Cloud. Also, in terms of galactic foreground extinction by interstellar dust, the northern CVZ at left has many more clear areas than the southern one. The southern one is clearly seen to be dominated by the Large Magellanic Cloud and galactic structures. A suitable field for time domain survey science with Webb at any orientation must be circular with a minimum diameter of 14 arc minutes. That size would accommodate simultaneously using primary and parallel instruments and doing these observations simultaneously with any of the 3 imaging instruments and at any orientation, and still allow for some leeway for dithering to cover the gaps between individual detectors. Webb's large aperture and sensitive detectors cause even rather faint objects to saturate. Now, deep saturation results in persistence, which reduces sensitivity, increases image noise, and it can mimic real sources in subsequent exposures. When persistence sets in, the photoelectrons that are accumulated during exposure are not all released upon readout and reset of the detector, but instead they are released more slowly over time in subsequent exposures. Because persistence can mimic real sources in subsequent exposures, it can be a source of sample contamination. Now, luckily, persistence from mild saturation is modelable and fully correctable, but this is no longer true for objects that are brighter than a magnitude of about 15.5. So a suitable field must be devoid of stars, point sources, brighter than this limit. Using moving viewport analysis, in which I accumulate near-infrared source penalties within circular viewports with a diameter of 14 arc minutes, and stepping through the entire CVZ area in both the northern and the southern CVZ, it turns out that there are very few regions of this size or larger that are devoid of sources brighter than magnitude 15.5. Like, ideally, these images should be blue with large patches that are good for deep surveys. But as I found, there's only very, very few patches of blue visible in here, the good parts, and essentially none are viable in the southern CVZ, whereas there are some clusters of regions in the northern CVZ. And the best one, the widest one, was located at these coordinates given here, somewhere towards the east of the CVZ, so about 3.5 degrees east of center. The very best region that was selected also has guide stars for Hubble, and it has a bright quasar that can serve as a phase calibrator for radio interferometric observations. And it offers a clean view out of our galaxy for extragalactic surveys, so low extinction. It is this region that was adopted as the JWST North Ecliptic Pole time domain field. Another good thing about a viable survey area would be if the zodiacal foreground emission doesn't vary much. Now, this criterion is automatically satisfied at the ecliptic poles. So I list it here, but it's not really a strong criterion. Using the large binocular telescope, a twin 8.4 meter telescope, and its prime focus cameras, I verified that this field was indeed exquisite as a deep extragalactic survey field, and owing to a relatively long sideline through the bulge, it's also a good galactic field. And it is indeed devoid of bright red stars. Near-infrared imaging with the MMT and very deep 3 GHz radio continuum observations with the VLA started the multi-wavelength observing campaign to characterize this new time domain field. And Dr. Christopher Wilmer took the lead on the MMT near-infrared imaging and also spectroscopy. The field center of the 3 GHz observations, I don't know whether a cursor is visible, but I mark in here the location of this quasar that can serve as a phase calibrator. It's a bit off-center. The requirement that that quasar is exactly in the center of the VLA observations makes that the entire coverage of the VLA is slightly offset from most of the other surveys. Nonetheless, the entire field proper is encompassed by the VLA data. The selection of the field and the initial observing campaigns to verify the viability of this new field were executed by a relatively small group of researchers. But subsequently, a strong community interest has allowed a rapid accumulation of additional observations. To develop this field as a community field, we are in the process of imaging it with the Hubble Space Telescope in ultraviolet and visible light, to which JWST is blind. In cycle 25, we imaged the inner portion of the field, where NIRCam and parallel NIRISS observations can overlap once you rotate the observatory over 180 degrees. In a large ongoing Ciclo Hubble program, we are adding a surrounding annulus to complete the UV visible coverage of the field. Webb is being readied right now for shipment to Kourou, from where it will be launched on the Ariane 5 rocket this December 18th, if everything goes according to plan. And then after a 6-month on-orbit verification and insertion into an L2 halo orbit, we expect the first GTO observations on this field to be executed in June of 2022. The community has proven tremendously supportive of this field. A loose and informal collaboration of astronomers all around the world, leveraging access to many of the foremost observing facilities, has accumulated deep and wide field observations across the electromagnetic spectrum, from hard X-rays all the way through long-wave radio, and from observations that focused on just this field to observations that provide the wider context of the JWST NEP time domain field. And to give you an idea, this table is a current snapshots of all the observations that were executed, are in progress, or have been approved for execution. The top portion of the table summarizes all the imaging observations, while the bottom portion lists the spectrophotometric and spectroscopic observations. And that includes the extremely wide 56 narrowband filter J-pass or JNAP observations. The current status of the Hubble imaging is summarized in this figure. The rosette of gray footprints represents the observations in hand, while the colored ones are the areas yet to be targeted. The complex overall pattern allowed us to reach a depth comparable to JWST in the smallest number of HST orbits. So each of these gray footprints corresponds to a 4-orbit CVZ visit with Hubble, and Hubble's and JWST's continuing viewing zones only partially overlap. That means that only 6 or 7 opportunities occur every year, and that means that the completion of this whole outer annulus takes a total of 2 years. So we expect that observations will continue for at least another year. Hot from the presses is here a composite of the Hubble observations of the field to date. A slide does not really do justice to this 20,000 by 20,000 pixel mosaic. It's almost impossible to display it properly. But the relative positions of the ACS and the Wide Field Camera 3 cameras are indicated for the first visit in cycle 25. So we use the fact that the distance between these two cameras in the focal plane of Hubble is 6 arc-minutes from center to center. And we dance these 2 footprints around the field center. Every CVZ opportunity is roughly 54 degrees away from the previous one. So in the course of a year, we can cover the entire inner portion in about a year in 7 or 8 pointings. And then the outer annulus, when we step again with 54 degrees around that outer circle, you cannot fully fill in 1 year. It takes 2 years, 13 individual pointings to do so. There's also a little bit of ruggedness to this pattern, and that is because we chose this field to be empty of bright stars. And that also means that it's empty or relatively devoid of stars that could potentially be used to guide the Hubble Space Telescope. So in some cases, we had to move over the field from the ideal position a little bit in order to accommodate having at least 2 good guide stars to guide on. And during a 4-orbit CVZ visit, we only acquire the guide star once, and then we keep it in the field of view at all times while we go around the Earth. So we really get the full orbit to fill with science observations in this case, and we don't lose time for reacquisition of guide stars. In this image, I zoom in a little bit, and the very brightest source that you see here is in fact the quasar that serves as the phase calibrator for the VLA observations. But there's a great variety in color and in shape of the distant background galaxies that you see there. So this is on par with the deeper candles observations in the good south field. So we expect to reach of the order of 29th magnitude AB magnitude in the F606W filter, and slightly shallower in F435W, so the B filter, and the UV filter. The UV filter should reach to about 27.3, then 27.4 magnitudes in areas that were observed only once. There's regions of overlap between individual pointings where we go deeper because we have twice the exposure time. So the Webb GTO, the guaranteed time observations of program 1176, PIS Roger Windhorst, will initially provide 8 filter coverage with NIRCam, partially overlapping with NIRISS 2-micron slitless spectroscopy taken in parallel, of 4 orthogonal spokes within this field. We will not cover the entire field. Each GTO spoke corresponds to a separate visit of 2 dithered pointings. But the actual orientation of this pattern on the sky will depend somewhat on the earliest date that science observations will commence, and can differ by up to 15 degrees from the pattern shown here. The GTO observations serve to provide 8 filter source characterization and a first look at time domain science in this field. It will be up to the community to fully develop this field with Webb and with other instrumentations, and to initiate time domain monitoring. The GTO program itself will only provide limited time domain coverage, typically no more than 2 or 3 epochs. The 2 rightmost panels show just a notional implementation of surveys that would yield expanded coverage up to a maximum of about 154 square arc minutes. But there's also other solutions where the GO spokes would abut the GO spokes and produce more like a cross shape pattern, or almost a square. So in conclusion, the JWST Webb can do ultra deep time domain survey science, but only in a few very special locations in the sky. And the best field to do so is the JWST NEP time domain field. It will be a 14 arc minute diameter community field, and the first JWST epoch at 4 orientations will be provided by the interdisciplinary scientist Roger Windhorst as a GTO program, and panchromatic ancillary data from radio to X-rays is already in hand. So if you're moved by moving objects, or if celestial beacons that vary in brightness are more your style, then this field is for you. In the second part of my talk, I will introduce and give an overview of some aspects of the Nancy Grace Roman Space Telescope, Roman for short. Roman is a NASA space observatory that's currently under development, and it should be launched sometime in the mid-2020s, maybe mid to late 2020s. It was previously known as the Wide Field Infrared Survey Telescope, but now has a proper name. It's built around an optical telescope assembly with a Hubble-sized 2.4 meter primary mirror. but with a 3-mirror Anastack matte optical design that gives it a 100 times larger field of view. Roman is designed primarily to perform wide field imaging and slitless spectroscopic surveys of the near-infrared sky. Much of its 5-year primary mission will be devoted to 3 large public surveys, the data from which will be immediately public, without any proprietary period. And the design life of the mission is 10 years, so we hope that it will just live forever like Hubble does. Roman was the highest ranked mission in the 2010 US Decadal Survey of Astronomy and Astrophysics, and was supposed to follow and complement flagship missions like Hubble, Chandra, Spitzer, and Webb. The science teams that guided the design of the Roman Space Telescope are to measure dark energy, and if not measure, then at least characterize it to high precision. It is to investigate exoplanets and also to conduct general great observatory astrophysics and planetary science, just like Hubble did. The Roman core community surveys within this primary mission, this 5-year primary mission, consist of a high latitude wide area survey of approximately 2,000 square degrees on the sky, and likely divided over more than one contiguous area, to provide imaging and spectroscopy for high precision cosmological measurements using weak lensing and galaxy clustering as the main techniques. A high latitude time domain survey of 5 to 20 square degrees with a 5-day cadence should enable the discovery and light curve monitoring of thousands of type 1a supernovae to a redshift of about 2. And the third survey is a galactic bulge time domain survey of somewhere in the neighborhood of 2 square degrees with a very rapid cadence of 15 minutes. And this will enable the discovery of thousands of exoplanets at AU or larger separations from their host stars, and they use the technique of gravitational microlensing for that. But nonetheless, about 25%, a quarter of the time of this 5-year mission is reserved for general observer GEO programs. The Roman Space Telescope has only one science instrument, the Wide Field Imager, WFI. And it has a technology demonstration instrument, the coronagraph instrument, but that does not have the status, the full status of an instrument, of a science instrument. Nonetheless, it will hopefully prove the feasibility of extreme contrast coronography from space. The Wide Field Imager is the instrument with the very large radiator on the right side of the optical telescope assembly here. It houses a massive focal plane array of 18 infrared detectors arranged in roughly in a 6x3 pattern as seen in the panel on the right. Its wavelength coverage ranges from roughly the V-band, the optical V-band, all the way to about 2.3 microns. So it extends the wavelength regime significantly compared to the Wide Field Camera 3 IR camera on the Hubble Space Telescope. Roman WFI also has a 15 to 20% higher throughput than Hubble, and that will help execute these surveys in a fast cadence as well. Last, the Roman point spread function is critically sampled in the reddest filter, the F213 filter. It's about a K-band filter. The pixel size of in the detector is a bit coarser than that on Hubble, but since it's an infrared optimized telescope, effectively we'll have the same number of pixels per PSF fluid half max as we're used to with Hubble. Roman overlaps both the red part of Hubble's and the blue part of Webb's wavelength coverage. Roman is optimized for wide field imaging and slitless spectroscopic surveys, which is a different optimization than either JWST or Hubble. The mirrors are indicated, the mirror sizes are indicated on the left, and it shows indeed that Roman and Hubble have identical sized primary mirrors. But the field of view, the instantaneous field of view of one pointing with Roman, is equivalent to 100 Hubbles. So in a pointing, for example, on the Eagle Nebula, we would not just get pillars of creation, but we get an entire galactic star forming environment. Larger stellar nurseries, like the Carina Nebula, have multiple bursts of star formation, where earlier bursts influence how the later bursts take place, or the later star formation takes place. Roman will provide a panoramic window on this stellar life cycle, all the way from the birth, the earliest condensations of stars, to the explosive ends, symbolized here by Eta Carina Homunculus Nebula. Roman will sample not just a portion of a nearby galaxy, but its entire halo environment of globular clusters and satellite galaxies, as well as getting distant background galaxies for free. A single Roman pointing is also well matched to the extent of typical galaxy clusters in the local universe. And this allows sampling the morphological mix, or the changing morphological mix of galaxy types, as a function of distance from a cluster core. An exciting possibility is that we would be able to get 100 times wider Hubble Ultra Deep Field, and that snapshots with this camera are equivalent to in area and depth to a whole candle's field. I don't know whether this is visible on your screen, but there's a tiny little footprint in the center that indicates the Hubble Ultra Deep Field. And around it is a jagged footprint that corresponds to the wider and somewhat shallower Hubble survey area around it. But getting 100 times larger area in one shot offers the possibility of sampling not just small portions of a square degree, but sampling square degrees. Roman is also equipped with two modes of slitless spectroscopy, through either a prism or a grism. Every object within Roman's field of view is dispersed by, for example, the G150 grism into a spectrum with a resolution of about 600. The only thing you have to realize with this slitless spectroscopy is that every pixel in the background also gets dispersed. So that creates typically a higher background than you're used to with slit spectroscopy. And that makes this technique particularly useful for detecting objects with either emission from lines, line emission, or continuum breaks. And as an example, a fairly faint galaxy is simulated how its light would get dispersed. And what is highlighted sort of in the middle of that spectrum is that you see an image in H alpha of the entire galaxy. So you can follow, you can trace the spiral arms in H alpha of that particular spiral galaxy. When this project was still an unapproved or more like a pipe dream, there were solicitations for science investigation teams. And one of those teams is the Cosmic Dawn SIT. And the PI of that SIT is James Rhodes, now at Goddard Space Flight Center. And those SITs were there to provide input to the project to optimally enable GEO surveys with Roman. such as a survey to characterize the epoch and the speed and the inhomogeneity of cosmic reionization, and to identify the sources responsible for reionization. Now, there is no guaranteed time associated with memberships of these SITs. It's a strictly advisory role. The GEO surveys will all be competitively solicited. But at least we hope to make sure that the capability for this slitless spectroscopy was there and was optimized for detecting Lyman alpha all the way from redshifts 8 through 11. Right now, the project, or I think less than 2 weeks ago, the project issued a request for information, RFI, for early definition astrophysics surveys that require up to 700 hours of calendar time to complete. And I provide a link here. If you just go to roman.goddardspaceflightcenter.nasa.gov, you'll also find a link to this solicitation. So if you are interested in in surveys, large surveys with Roman, and that might be on the JWST North Ecliptic Pole time domain field, but you may have other ideas and better use for it, then I would encourage you to take a look at that and to submit a proposal. Because Roman can probe very deep, very far back in cosmic time. It can probe all the way to the epoch of reionization, and hydrogen in the intergalactic medium was still partially neutral. And it can sample regions of both high and low galaxy density and both high and low neutral fractions, all in one survey. So this allows putting direct constraints on cosmic reionization to quantify the neutral hydrogen fraction in the intergalactic gas and its topology at the central phase of reionization. And one set of tests that we've been thinking about in this Cosmic Dawn SIT uses Lyman alpha. It can use directly the average strength of the line emission. Since Lyman alpha is resonantly scattered, it will be suppressed by a factor of more than 3 if there's a neutral IgM present. And it is sensitive to neutral fractions that are larger, typically larger than 10%, than other probes like CMB polarization or the Cohn-Peterson test, which typically probe neutral fractions of less than 1%. One can also use the statistics of Lyman alpha line detections in samples of continuum selected galaxies. Now, especially for this test, it's so important that the field of view is wide and that slitless spectroscopy is available, because it is uniquely powerful in providing the needed unbiased samples and secure both the characterization of the objects and robust redshifts. One can also use the clustering on the sky, the angular clustering of Lyman alpha emitters, to probe the progress of reionization. In the intermediate phases of reionization, the ionization bubbles in the IgM did not yet overlap. So Lyman alpha emitting galaxies should show an enhanced angular clustering. And an example of that is seen in this simulation where typical footprints of the Hubble Space Telescope and 2 abutted footprints of the JWST NIRCam are shown, as well as the much larger footprint of a ground-based telescope, the Magellan telescope, and its 4-star camera. Now, even while Magellan and this camera is able to average over cosmic variance, it cannot probe as deep and as faint as either HST or JWST can. But as an illustration of the importance of cosmic variance, there's 2 JWST footprints of NIRCam shown here, but with one that happens to fall on an overdense area with 15 Lyman alpha emitters, whereas the other one right next to it has 0 Lyman alpha emitters in an underdense region. And these simulations came from the work of Tilvey et al. 2009. If we use observed Lyman alpha emitters, such as the Redshift 2 Lyman alpha emitter discovered by Earp, or measured by Earp et al., and simulate how a Roman slitless grism observation of very similar, intrinsically very similar Lyman alpha emitters would be if they were at a redshift of 8.5 and at a redshift of 11, assuming that we have about 30 hours of total integration time and a continuum flux level that corresponds to about 26 magnitudes or thereabouts. And that the rest frame Lyman alpha equivalent width is typical, about 60 angstroms wide. Then it turns out that you can detect with Roman a redshift 11 objects this way. And not only detect that it is a redshift 11 object by unambiguously identifying this line as Lyman alpha, because redward of Lyman alpha, there is a non-zero continuum, whereas blueward of Lyman alpha, it's consistent with a zero sky background. And simultaneously getting the redshift, then you have enough information to place this galaxy in a 3D space rather than just project it onto the sky. So we know at which redshift, and we know how much Lyman alpha is being emitted. And the expectations are for the kind of surveys that are planned, either public surveys or geo surveys, in the case of geo surveys proposed, then you should be able to detect hundreds, if not thousands, of these objects. Maybe not quite at the redshift of 11, but it should be a statistically large sample. No, I seem to have lost my last slide. There we go. So in conclusion of this part, Roman is capable of providing the equivalent of hundreds of Hubble ultra-deep fields, with wavelength coverage that extends further into the near-infrared than accessible to Hubble Wide Field Camera 3. And that allows Roman to find very rare and very faint objects with very low surface densities on the sky, and provide both detection and source characterization through slitless spectroscopy. The Roman project is currently soliciting input from the community for potential surveys of up to 700 hours of calendar time. So I encourage you to look that up, and with this I would say muito obrigado, and I'll be happy to answer questions.
Okay, thanks, Rolf. That's a very, very interesting talk. Let me see. I'm not accompanying the YouTube, but let's see if there are questions from the attendees.
Yeah, Ricardo has raised his hand.
Okay.
Okay. So I promoted him so he can ask his question.
There we go. Hi, Rolf. Nice talk. I was just wondering about the first part on the JWST. With so many single epoch images, if you plan to do some sort of co-ed, and what do you expect from that?
As long as you do not hit the natural confusion limit, co-adding will get deeper. You will find fainter objects. If your goal is to do time domain science, then you always get for free at the end of your project also a deeper image by co-adding everything that doesn't vary. So in many ways, this is a win-win and a great legacy value of these time domain surveys. I don't know whether that answers your question.
Right. Yeah. So so you expect some trouble from so many faint sources raising from the background, right? So
yes.
Okay. Yeah. Cool. Great. Cool.
So
Thanks.
it will not, in all likelihood, it will not just scale as the square root of the exposure time, because there will inevitably be some sources lost or undetectable because they are covered or overlapping with other objects.
Cool. Thank you.
Okay. Let's see here. There are no hands. I had a couple questions, Rolf. So with respect to the JWST, I'm not sure I understood exactly. Well, one thing that was curious was what's the persistence time scale? But I guess you're avoiding persistence anyway, right? So it doesn't really matter the time scale.
Right. I think Christopher Wilmer can answer this better than I can. Luckily, the longest persistence time scale, the ones that would be hours, is not as severe or not even significantly present. This was originally feared, but there's still the shorter persistence time scale that we will have to deal with. In the pipeline analysis of the Hubble data in the archive for the Wide Field Camera 3 IR, they do tend to figure out what bright sources were observed in the hours before a given observation was observed, and they can correct for objects that shouldn't be there, that are only a manifestation of persistence. The hope is, and I think that NIRCam does not have as bad a persistence for things that don't deeply saturate. So as long as the saturation is mild, you will not get into too much of a problem with uncorrectable persistence. But as soon as you get to, to be clear, regular saturation sets in already at about 19th magnitude or so, 18.9 in some filters, if I remember correctly from the top of my head. And we're talking about 15.5 magnitude. So that's deeply saturating the detector.
Okay.
Yeah,
that's what we want to avoid.
Yeah, I can pitch in here. So from what we know from the engineering data, you can actually have very little effect of persistence after an exposure. Once you have the readouts and the reset, it should not be too bad. But for sure, we're only going to know this once we start commissioning.
I'm assuming it gets significantly worse as you go to the far infrared, the filters down there.
Well, it depends a lot on the width of your filter.
Okay.
But, with James Webb, you can actually, let's say if you want to target a really bright object, you can go to subarrays. And that way you read out much faster and you don't have the build up time to have lots of persistence. And you also have the continuous reset. But yeah, if you have a really bright star in the field, that's one thing that we don't know. But on the other hand, most of the deep fields have been selected, so there are no really bright stars in them.
Yeah, okay. So just one last question on the JWST, but since we're talking about timescales, is there a risk that the JWST observation of the NEP are done before the HST extended version of the HST is obtained?
Yes. In all likelihood, there will be at least 2 pointings that will not be done yet when the first JWST data comes down. If I remember correctly, there is a pointing in July and a pointing in September that are still part of the Cycle 29 program. And the hope is that we will be able to get the first data from JWST in June, end of June.
Mm-hmm.
And unfortunately, this is unavoidable, but we will have coverage for most of the field. And we can get lucky. Like if the orientation of the pattern on the sky is such that it only overlaps areas where we already have HST data, then there's no problem.
Right.
It's
so if I
only
understood correctly, your image, the very center is not, there's a lack of overlap in the very center of the field, or I misunderstood that.
Yes, there is in the pattern with JWST, there is a natural hole. It's a small hole. I think it's of the order of an arc-minute or so, but it's unavoidable, again, because of the distance of the two instruments in the focal plane array of JWST. Unfortunately, we cannot make them move closer to each other, in which case we could fill this hole.
Okay, thank you.
There is an alternate layout for an extended GO program, where instead of rotating the whole field around this pointing center and just keeping that hole, we lay out two pointings with exactly the same orientation and exactly the same shape as the GTO pointings, such that you get a three spoke wide area. And if you then rotate that over 90 degrees and 180 degrees and 270 degrees, you will actually fill that hole, and that becomes an ultra deep field, because it then starts overlapping in all the, or a significant number of the individual exposures. So there is something to be said for not just rotating this pattern around, but for more like a staggered pattern.
Okay.
In that case, by the way, there is like 4 corners that stick out of the circle where you will not have coverage in all likelihood with HST, but there should be coverage from Chandra, XMM, New Star, and ground-based observations.
Right. Well, I was asking about we're going to talk offline about this, but I was asking about the hole because as the X-ray detectors, well, they're not going to be pointing really to the center, because deep observations, they're going to be doing lots of small little dithering of the thing. So it's really not a big deal in that respect.
But to some extent, this is the new normal. With JWST observations, it's much harder to create contiguous patterns than it is with HST. HST is a relatively agile observatory. You can do a lot of things at non-optimal angles and still get away with it. With JWST, that tends to no longer work. So you will find patterns that have either small slivers of coverage missing or wedges of coverage missing. It will become more of a patchwork for many surveys, is my feeling. And in the end, for most survey signs, all you really care about is just aerial coverage. It does not always have to be contiguous, even though for press release images, it would be nice if it was.
Yeah. So, Simone, I cannot see the YouTube from where I am.
There is no question, no other question in the YouTube, in the chat.
Okay. There is Chris, did you raise your hand?
Yes.
Okay.
Is there going to be a calibration field like there was for Spitzer with Roman?
They have been talking about it, but it's still not quite clear. The actual implementation of the public surveys, I think it still has to be ironed out. There's a good chance that it will overlap one of the other big surveys like Euclid and LSST. Like if the instantaneous field of view was better matched to the 14 arc-minute area, diameter area of this JWST NEP field, then there would be a very strong case for making this the calibration field. The fact that you cannot have all the Roman detectors within this field made it less of a cell. It was considered, and this field is in many of the tables that you'll find in Roman documentation, but it never is at the top of the table. But things can change. We don't know. There's still, I would think, at least 4 or 5 years before we really have to worry about this.
So I was curious about the survey speed, because it is, of course, you have a much higher area than HST, but how, and I'm not exactly sure, and I'm very curious to see how they're planning to do the survey. From where you said there is no GTO, so are the surveys proposed by people, and you go from a survey patch here, another one there, or is there like an Rosita, basic survey of everything, and then opens for GEO requests?
It's a little bit, my impression is that it's a little bit more of the former than the latter. So there will be contiguous periods of time that are reserved for one of these public surveys, but then for specific observations, the other observers, the other survey programs can cut into that. And there is this strain between, say, the supernova survey, the high cadence, high latitude survey, and just the survey area survey at high latitude, where the number of constraints that are put in putting a schedule together are mind-boggling to me. I don't know how they are going to schedule this telescope.
Mm-hmm.
It's going to be very complicated, and I wouldn't be surprised if eventually no human will be in the loop for it.
Yeah, that's not a trivial matter. Even in JPass, to try to actually get the proper area efficiently,
Right,
without the corners and wasting time, because you can significantly reduce your survey speed if you don't do this careful. And
right. But
imagine
because
having
of the orbit, effectively, Roman will make a round around the sky in 1 year, just like the Earth does. And during that time, it has an annulus of observability, just like JWST does, just a wider one. And that restricts what you can see at any given time. So if you want to do high cadence observations of the galactic bulge, then that needs to be within that continuous viewing area or that annulus at specific times of the years. There's no way around that. So that survey has to happen when the bulge is visible. On the other hand, supernova may go off somewhere, or a whole bunch of them, that need to be followed up. That requires butting into this program, and that creates a strain between the different surveys. And in early conferences about this, there were very heated debates about whether or not a portion of the survey would be entirely lost if you lost 1 day out of a schedule of 2 weeks, for instance.
Mhm.
And I don't know whether that is resolved.
Mhm.
In my mind, the large area high latitude survey is the easiest one to just schedule whenever. And there will be holes in it will not be contiguous entirely, but you can get large swaths of contiguous coverage or stripes of contiguous coverage. So in that sense, I think it's the one with the least constraints. I think the time domain ones are the ones that are the most difficult to satisfy, especially if there's 25% of GEO observations that somehow have to be scheduled in between these longer campaigns as well. So depending on what GEO proposers want to observe, there may be more or less strain or more or less conflict with these other surveys.
So what exactly then did they expect? Because this address that you sent there, this place that we can send, suppose I have an idea for a survey. That's what exactly is this, first of all, is this binding at some level, or suppose the idea is good? Is it somehow binding? And second, if the survey strategy is not defined yet? So what do they expect?
I think the expectation right now is more at the level of a white paper than at the level of an actually fully implemented survey. I don't think you'll get any money for it. So in that sense, also, it's a whole lot less binding than if there was money involved.
Right.
But it allows the community to set priorities. It can, for instance, say, well, okay, we find certain geoscience more important than one of the 3 public surveys. If that's the outcome of this exercise, then that's a very important outcome. On the other hand, it may be that it says, well, nope, these public surveys, they must be done in the first 3 years, and then we'll figure out what else we can schedule. That would be a completely different outcome. I don't know which way that would go, but it is the kind of input that the project is soliciting. They need to know sooner rather than later.
Right. Okay. Very interesting.
But in a sense, scheduling a telescope like Hubble is very much easier than scheduling a telescope like JWST or scheduling a survey telescope like Roman. It's pretty much the leeway that you have in off-nominal pointings, the leeway in getting to different regions of the sky fast, being able to dump angular momentum in the magnetic field of the Earth, which you will not be able to do in L2. Things like that, they all make these spacecraft quite a bit more complex than Hubble, and Hubble is already complex.
Okay. Any more questions?
No, I think no. No, on YouTube, no.
Okay, so we are past just a few minutes after the time, but that's okay. And so I'd like to thank you, Rolf. That was extremely interesting and very exciting talk. The information that you passed is very, very cool, and we're gonna check out the link that you sent. Maybe they actually have some more details about what the constraints are for the surveys. And
yeah, there's quite a lot of documentation that was put on the main website there. There's also you can also get there from STSCI webpage as well, and they have links to the various white papers, but I've not seen anything yet that would qualify as a completely worked out schedule.
Mhm. Okay. In any case, thanks again for presenting. You and Chris, it's very cool talks.
Okay.
And talk to you soon, I guess, when we get some news about the NEP on our side.
Right.
Thank you, Rolf.
Okay. Bye-bye, Simone.
Bye-bye.
Bye-bye.
Bye-bye, Renate.